Hi everyone! In this project I wanted to create a Verilog implementation of the Kalman estimation algorithm. The experimental set point includes a PC running a MATLAB script that generates a waveform, adds some noise uniformly distributed with zero mean value, and sends a sample to an FPGA of the Altera DE2 board via UDP packet, in which is an iOS2 microprocessor instantiated on that receives the packet, and with the internal instantiated Kalman ELU module filter the signal and send back the result to the MATLAB script. Instantiated on the FPGA, there is also a control unit that manages the timing of the ELU. Okay, now let's see some about the algorithm. From the knowledge of the variance of the measure and the process, and the last step, covariance and estimate measurement, we can do a prediction, a priori covariance and a priori measure estimate. Then we can calculate the Kalman gain, and upon the measure receipt we can do a correction to calculate a posteriori covariance and a posteriori measurement estimate. The algorithm is iterative and is well suited for implementation on embedded system to processing data streams. Let's take a look at the Kalman ELU implementation. These are the operations arithmetic implemented on the Kalman ELU. Here we can see the input register of the sample, and here the two output register, one for the covariance and the other for the estimate of the measure. The entire project is based on a 32-bit architecture with signed operation, so we can evaluate the negative number too. After we have the implementation in Verilog, we can simulate with a test bench that generates a waveform, and in particular we can see the signal that the microprocessor sends to the control unit. The microprocessor loads new measure and sends the start signal to evaluate the measure. Immediately the control unit responds with the basic flag high, and when it turns to 0, the evaluation is done, and the processor can clear the start flag, load new data, and send back another data to be evaluated, and so on. We can see the estimate of the measure and the estimate of the covariance. Okay, now let's take a look at the demonstration. Okay, we use the software Wireshark to monitor the transmit of the packets in the network, and the MATLAB script that open a UDP communication, generate some kind of signal Here we can see a ballistic trajectory of a missile. Adds a noise uniformly distributed with zero mean value. Write the data on the socket and wait for the receive. Finally, graphic results. Okay, on the right we see the C code that is executed by the NIAS2, the initialization, the UDP packet receiving routine, the evaluation of the sample, and the transmission of the results. Okay, we can start. Now after the reset, we should see that it awaits the measurement to the measure to be processed, and then we can launch the script. Okay, it's evaluating. Okay, at this point, we see that two UDP packets are passed through. Let's see where they are. Okay, here they are. The first, with the source address IP.5, which is the PC, and the destination .200, which is our FPGA, containing the payload with the data to be processed. Our script has received the measure and printed them, have evaluated them one by one with obtainment of the measure estimate and the covariance estimate, and then he sent back the results via UDP packet. Here we can see the transmitted packet. Okay, here it is. The source this time is .200 from our FPGA to destination .5, which is our PC. Okay, now it said evaluation complete with success, and the MATLAB can we plot the results. In particular, we can see in light blue the signal ideal locally generated by the script. In dark blue, the noisy one, and in green, the software Kalman FIlter locally calculated by the script, to compare with the red one, which is the hardware one calculated from our FPGA. Below we can see the covariance estimate sample. Okay, we're done. As usually, I give you all the necessary material to test it out at home, and if you have any question, just leave a comment. I hope it was interesting. Hello to everyone.